So in this session, we're going to have 6 talks, and each presenter is going to have 10 minutes. They'll present their screen, and we'll do a brief recap of their talk, and then take questions and answers. We're not doing jury for this session, so please feel free to unmute, discuss, ask your question. It's supposed to be more interactive. So we're going to start with Yishong from Emory University. Can you present, please?
Thank you for the opportunity to introduce our work on federated tensor factorization, which is the focus of my recorded talk. But today I also added a couple of slides on federated analytics because based on our breakout session yesterday, I thought it might be relevant and of interest. So this is a joint work with students and collaborators at Emory, UT Health, University of Arizona, and Baidu and Kyoto University. For the federated tensor factorization, our problem setting is the cross-silo data analysis, where the data are horizontally distributed at multiple sites, for example, multiple hospitals. And the goal is to do a collaborative tensor analysis while keeping the data private at each local site. So the federated tensor factorization framework is very similar to the federated learning framework, where the local sites do the local factorization and only send the intermediate feature factors or their corresponding gradients to the server. However, what's interesting, what makes it different from the federated learning is that this multi-factor or multi-block structure presents some interesting challenges or opportunities. So in our previous work, one of these I actually presented in last year's workshop. We developed 2 different optimization methods to enforce the consensus among the local feature factors, including the ADMMM approach and the elastic averaging SGD approach. So in our recent work to utilize the multi-factor structure of the factorization and to further enhance the efficiency, we proposed a new approach called block randomized SGD. So the main idea is in order to reduce per round communication, instead of sending the full gradients of all the factors, we basically just send the partial gradients of a randomly sampled block or factor. In addition, we also do the gradient compression combined with error feedback, which has shown success for distributed federated learning. And finally, it also reduces the communication frequency by periodic communication, just like the local SGD or federated averaging. So our main theoretical result is that given this combined communication reduction strategy, we can indeed achieve the communication reduction without compromising the convergence rate. And here just shows a very quick result that compares the different communication reduction strategy in terms of the loss with respect to the communication cost. I know it's a lot to look at, but if you just look from right to left, the rightmost is the baseline, the most expensive approach using full communication. And from right to left, we can see each communication reduction strategy helps reduce the communication cost. So in addition to the efficiency, of course, privacy is another challenge. In our previous work, we enforced differential privacy by adding factor perturbation, basically perturbs the intermediate factors before they're sent to the server. Our hope is that given the new communication efficient strategy that we developed, we should be able to develop more efficient or more effective privacy mechanisms, taking advantage of the inherent benefit of the communication efficient techniques in terms of privacy. More generally, I think there's a very strong synergy among efficiency, privacy, and robustness, as highlighted by many talks yesterday and today. For example, for privacy, the communication efficient techniques such as the compressed per round communication means reduced sensitivity, which means less noise should be required if we want to guarantee the same level of differential privacy. And the periodic or less frequent communication means less accumulated privacy cost or tighter privacy composition. So I think we should really explore this synergy to develop mechanisms that have better trade-offs. So that's for the federated tensor factorization. To switch gear a little bit, as I mentioned, I added a couple of slides on our recent work on federated analytics under local differential privacy. So one particular application we looked at, I mentioned yesterday, is the frequency and mean estimation over key value data. One example is each user can have a set of movies they watched and the corresponding ratings. So the goal of the aggregator is to estimate the frequency of the movies and the mean of the value or mean of the ratings. If we do this in a naive way, basically perturb the keys and values separately using the standard LDP mechanisms, obviously by ignoring the correlation between the key and values, it's going to have less than optimal utility. So the main idea of our work is to try to exploit the correlation between the key and values, and by using a correlated perturbation scheme, we're able to achieve better accuracy or trade-off of the utility and privacy. And as we work on different applications, we also realized the LDP notion can be strict or can be less flexible sometimes. And many work actually have explored how to improve the utility and privacy trade-off in terms of LDP. And one line of work is to explore the different notions or variants of the notions to relax some of the restrictions of LDP. So one particular observation we have is that for different records, sometimes they have different sensitivity levels. For example, for website click records, some websites may be more sensitive than others. So if we can allow the users to specify, or the system to specify, different privacy level or privacy requirement for different input, we may be able to offer a better privacy and utility trade-off. So we proposed the input discriminative local differential privacy notion called ID-LDP. To allow that. This figure quickly shows the comparison with some other related notions in terms of the policy graph, where each node is a different data input, and each edge shows the indistinguishability level between the pair of inputs. So we can see the personalized LDP provides the user discriminative protection, and the geo-indistinguishability for the location-based applications, and the condensed LDP provides a distance discriminative protection. And in contrast, our notion provides the input discriminative notion. Basically, each input can have a different privacy level, and the indistinguishability level between a pair of inputs can be determined by a function of the two privacy requirements. For example, can be the minimum of the two. So our result basically show it offers better trade-off in terms of utility and accuracy, utility and privacy. So I will stop here and happy to take any questions or comments. Thank you.
Yeah, we have about 3 minutes for questions. I'll ask a question. In fact, I have 2 questions. The first one is, for the analytics application that you talked about, do you assume a closed set or an open set? In other words, do you assume we know all the movies, or we're trying to discover these movies and then compute their frequencies and ratings, average ratings?
That's a great question. So here we do assume a closed set.
Okay, so it's like a histogram and then mean estimation and histogram estimation.
Exactly, yeah. The main interesting thing here is just the correlation between the key and values, but the key is a closed set. Yeah.
Yeah. The other question I had is on the last slide. Your input discriminative LDP.
Yeah.
Be very closely related to a new notion of LDP we recently published at ICML. It's called context-aware local differential privacy. We not only show in experiments that we get improvements from encapsulating the context, we also do some theory to prove that you get order improvement compared to the vanilla LDP. That's just, I wanted to bring this to your attention.
Oh, that's great. That's great. Yeah, I would definitely check it out.
Yeah, there's also a recording on our workshop website about that work by Tang Sun. Let's switch to the next speaker. Next, we have Aurélien.
Thanks a lot. So I'll try to give a quick overview of our work on distributed differentially private averaging. So the setup is the following. We have a set of n users or parties. Each user holds a private value, xu, which here we assume is a real value between 0 and 1. And then the goal is to accurately estimate the average of these values while guaranteeing epsilon delta differential privacy. The motivation for looking at this problem is that it is a key building block in essentially many federated optimization algorithms, where at each round, users make a local updates, and then these updates are aggregated together. So we propose a novel protocol which has 3 key properties. The first one is that we can achieve trusted creator utility. So this is unlike local differential privacy. And we can do that with a logarithmic number of messages per party, which is unlike classic secure aggregation methods, which require all pairs of users to essentially exchange some kind of mask. And finally, we can guarantee correctness against the presence of malicious users. So let me present quickly the protocol itself, because it's actually very simple. So we really consider a graph over the users. And so the first step of the protocol is that all pairs of nodes that are connected in this graph will jointly generate a pairwise canceling Gaussian noise. So this is a Gaussian distributed value that one user will add and the other will subtract. Then each user will independently generate some Gaussian noise with a different variance. And then each user reveals the sum of its private value, the pairwise terms, and the independent noise term. Okay, this is this red term here. And so it's easy to see that from this, we can construct an unbiased estimate of the true average by just averaging these outputs. And the pairwise noise essentially cancels out, and we simply remain with the variance that is due to the independent noise terms. So what can we say about privacy? So first of all, let me clarify what is the threat model. The adversary here is a proportion of 1 minus rho colluding malicious users. So essentially, they observe all communications that they take part in, but we assume that other users, which are honest but curious, communicate along secure channels, so malicious users cannot observe the content of their exchange. And what we show is that our protocol achieves epsilon delta differential privacy with trusted creator utility when two conditions hold. So first of all, the subgraph of honest users must be connected, and then the pairwise variance must be large enough. Okay, and how large it must be, essentially, we show it depends on the topology of the graph, and in particular, in how nice a spanning tree is embedded in the subgraph of honest users. So these are general results that we can then instantiate to specific cases. And here's an example of a more practical result where the graph is generated by having each user randomly pick k other neighbors uniformly at random, where k is of order log n. Here, the second dot is the independent noise variance. We set that in the same way as what we would do for the Gaussian mechanism in the trusted creator setting. And then the pairwise noise is a function of that, and also depends on k. So the more neighbors you pick, the less pairwise noise you need. And then we can show that under these conditions, we can achieve epsilon delta differential privacy with trusted creator utility and this logarithmic number of messages per user. So here I have used big O notation for simplicity in this theorem, but I want to emphasize that we essentially track constants. So our theoretical results, they really give practical values for k and these pairwise variants that are sufficient and that remain quite small in practice. So you can check the paper for examples. The last part of the contribution is about ensuring correctness. So the privacy doesn't really depend on what malicious users do, but the utility can be compromised by malicious users who could tamper with the protocol, sending incorrect values, for instance. So what we do is essentially enable each user to be able to prove some properties about its values and the computations done in the protocol without revealing additional information. This is done using crypto primitives, in particular Petersen commitments, and on top of which we build some zero-knowledge proofs. And the sumness of these proofs, they rely on this classic crypto assumption, which is the discrete logarithm. We can furthermore prove some consistency properties across multiple runs when you run multiple averaging across similar or the same data, and also handle dropout to some extent, but I don't have too much time to talk into that now. That's it, so I'm happy to take questions.
Thanks, Aurélien. I have some questions, but I'll let others go first. Tirtha, I see you're unmuted.
How is this related to the secure aggregation or homomorphic encryption protocols which operate on like a field? I think the idea is very similar, but somehow...
Yes, that's a very good question. So, okay, so first of all, so in this work, we don't do secure aggregation per se. So the final goal is to do differentially private averaging. And in fact, we don't go through the intermediate step of doing secure aggregation. So because this pairwise noise is Gaussian, it has finite variance. So it doesn't satisfy the requirements of secure aggregation. Yet, of course, with secure aggregation, you can combine that with adding some noise in some way to get also trusted creator utility for for averaging a little bit like we do. So the main difference. Okay, things are not so easy to compare for this reason, and also the settings and Phet models are not always the same. But I think the classic approach in secure aggregation would have essentially either require some strong assumptions of like maybe public randomness, or they would be very costly in terms of having this quadratic computation and communication overhead. Okay, so that was true until very recently, because we have seen a couple of papers, including from some folks at Google, that improve this upon this quadratic overhead, and with also some ideas that are similar to some extent. So I think that's quite interesting, and I think we need to do a more systematic comparison. The guaranteed correctness that we have, I think, is something in addition, at least to some extent. But yeah, making a very clear comparison is a bit tricky because the settings are different. We also don't assume a server. Yeah.
So Aurélien, on this note, with the new work from Google and other teams outside Google to reduce the communication and computation overhead of SecAg, because you also are relying essentially on this idea of not exchanging messages between all the users, right? There's this graph, and you only exchange messages with randomly selected neighbors. Do you now think that these new works imply that you can get better or stronger security and privacy without the overheads that you were trying to tackle in your work, or there are still some gains we can get from your approach?
I think they are okay to some extent. They can probably, if what you're interested in then is differentially private averaging in this setting, I think they provide similar guarantees. Okay, again, like the models are a bit the same, like the assumptions, but let's say the privacy utility trade-off and maybe roughly the complexity overall is probably similar. Again, the goal is a bit different, and so something that I think makes our work also a bit different is that we have this, again, like every type of noise that we add is essentially Gaussian, so it's in expectation it's 0 and it has finite variance. So we think this is quite interesting for robustness. So there are some cases where you might be fine with leaving a bit of residual noise inside, maybe because there was too much dropout or something like this, something unexpected happened. And you can still have some kind of utility guarantee in this case, because it's not just a binary mask that you put on top of the data. And if you're missing one, then you get completely nonsense, right? So I think this property is quite interesting. We don't exploit it maybe well enough at this point, but I think that's one of the key maybe differences, which comes from the fact that we don't do secure aggregation. We directly tackle this differential privacy, differential private averaging.
I had a follow-up question if we have still time.
Yes, 1 minute.
Okay. How much shared randomness is necessary for your protocol? Do you need like a shared source of randomness between every pair of users, or?
No. So we have to generate this randomness in a decentralized manner. Okay, so you can do that with this sort of commit and reveal type of protocols, but because only pairs of users that are connected in the graph have to exchange some random values, you only need the order is this much. So it doesn't scale like the number of like n squared, but it scales essentially like the degree of the nodes in the graph, and this can be done in decentralized way because there is no. They are only pairwise correlated, right? So yes, you don't need n squared randomness.
So I still have a question, but we're actually at time. I'll post it on Dory, so we can continue having these discussions on Dory. I think Adria also may have wanted to say something.
I'm sure. Yes.
Yeah, we can. Has a lot to say. In the interest of time, let's switch to Karn from Google.
Thank you.
And take over. Thanks, Aurélien.
So hi everyone, I'm Karn. I'm a software engineer at Google. I'm working on the Federated computing team, which works on the intersection of cryptography and different business problems that Google has. And we've worked very closely with the teams studying federated learning. And so today I'm going to talk about our recent work, which is called Pure with Default and Applications. And I'm just going to give a very quick flavor of it. It's with co-authors at Google and our intern from last year, Mi Chu, who's now a postdoc at Berkeley. So let me first describe what the problem is we're trying to solve. And just as a disclaimer, this is slightly off meta from the rest of the talks in this workshop, because we just have one user talking to a server and who's trying to answer some questions in a private way, to answer a particular question for the user in a private way, using data that's split between the user and the server. So the user, we're going to imagine the user has a bunch of IDs and weights. And a server also has a bunch of IDs and weights of like a substantially bigger database. And what we want is for the user to be able to compute the dot product of weights over the intersection. So for those IDs in common, the user should learn the sum of the corresponding weights multiplied together. And we want the user to learn this dot product with some noise added in order to achieve differential privacy. And the guarantee we want is that nothing more should be learned by either the user or the server. So the server shouldn't know which items were in common, and the user shouldn't know which other items were in the server's database. And why do we care about this problem? Well, there are several possible applications. So one is that it's actually a good fit for some versions of exposure notification. So you can imagine that the database on the user is a bunch of Bluetooth keys for people who broadcasted keys to this user, and also with some weights, which are like the signal strength. And the server has a bunch of Bluetooth IDs voluntarily uploaded by users who are sick, and also like a virulence weight, which is like how sick the user, how infectious the user was at the time. And so this dot product would allow the user to learn some kind of score of like how exposed they were to somebody who is sick, and could therefore get exposure notification based on the score. And of course, there's a privacy need here because you don't want everybody's keys flying around in the clear. You just want to learn whether it should be alerted or not. And another application is actually for something quite different, which is to measure ad effectiveness for online campaigns. So here you could have the merchant who has a bunch of user IDs and what values they spent, and an ad tech company who has a substantially larger set of people who've been shown ads, and a number which says how long ago the ad was shown, like assuming that the effect of the ad decays over time. And then this dot product over the intersection could be kind of like a weighted conversion credit for how effective this ad was in getting people to go to a store and buy something. And again, there's like strong privacy needs here. So our approach for this is to build a tailored multi-party computation protocol for computing this functionality, and we're focused on asymmetric set sizes. So the case for symmetric set sizes is already like really well studied, but asymmetric is really not that well studied, and we think actually really useful. And so I'm just going to give a very quick overview of how this solution works. And the starting point is something called private information retrieval. So private information retrieval is a protocol that allows a user who has an index to privately retrieve the ith item from the server's database without telling the server which item it retrieved. And this is kind of our starting point because it's relatively cheap for the user to query a single value. And it's expensive on the server, but we don't care because the server can do a lot of work. And so from this, our first step is to build what we call keyword peer, which allows the user, instead of querying an index, to query on a keyword or an ID, and to get back the weight associated with that ID. Now, this is actually not that hard to build, but it turns out that the problem that we have with keyword peer is that if the ID is not in the server's data set, then the user retrieves garbage. So our main contribution, or the most complicated part of the paper, is actually getting rid of this garbage.
I guess maybe in the interest of time, when Karn comes back, we can continue. Perhaps Dimitri, you can go, and then we'll give Karn time to resume.
Sure, sounds good. Let me know if I can start now if you want. But it says that he's presenting, so I don't know if I can.
You can take over, but yeah, I pinged him and he's not responding. So my assumption is maybe his laptop crashed or a browser or something.
All right. So Yeah, I will also. I'm having some Wi-Fi issues, so I will turn off the camera, I guess, while I'm presenting. But yeah, so let me just do that. And yeah, please let me know if you can see my full screen. Let's see. Oh, how do I do this?
Yep. So yeah, the bottom there's.
There it is. All right, there we go. Yeah. So can you see this?
We can see it.
All right, great. So I think I have 10 minutes. I'm gonna spend like 3 minutes on these slides. They're very few, but
We don't
yeah,
like,
I think it's.
we don't
sorry?
like what we see, but we can see it.
Okay. So yeah, so I think this is a nice follow-up to Vitaly's keynote yesterday. So basically, my group and I have been looking into understanding some robustness issues of federated learning, in particular the effectiveness of backdoor attacks. So a couple of years ago, there was this really cool paper by folks at Cornell Tech, including Eugene and Vitaly, that are attending this workshop, that basically said, look, you can basically hardwire some backdoors in federated learning models and make them mispredict on subtasks of the main whatever predictive set of tasks. For example, you can make them predict green cars or mispredict green cars as frogs and whatnot. And the way that they were achieving this is essentially by a technique called model replacement that adversarial nodes can achieve at some points during the learning process. Then there was a paper by Google. A bunch of you guys are here, and then you said, "Look, yeah, this is true, but there are some issues with these attacks, and either they do not persist, meaning that after they're inserted, they kind of like are washed out during federated learning, or there are sort of simple methods that you can use, like norm clipping mechanisms and differential privacy, to essentially overcome them." And there's been a lot of very interesting work in this area, very reminiscent to adversarial examples where there's kind of like, there's backdoors and defenses and backdoors and defenses. And I think the verdict is sort of still out of, can we really backdoor federated learning, right? So in this paper, which is currently on archive, we essentially give theoretical and practical, let's say, indications that there are some unavoidable weaknesses in training federated learning models. So from the theory perspective, what we saw is that, if a federated learning model is prone to adversarial examples, then you can prove that it is prone to backdoors. So the main point of this first theorem is to say, look, if you claim that you're fixing backdoors, you're probably also fixing adversarial examples in the general case, and that is an open problem. So what essentially this theorem says is that it's unlikely to resolve one without resolving the other. The second theorem says that even detecting in the general sort of worst case setting, detecting the presence of a backdoor can be, 3SAT is reducible to that. So it's an NP-hard problem. And of all backdoors, those that are essentially affecting a small measure of the input space are also hard to detect using first-order methods. So if you were going to use like a gradient-based type of method to detect backdoors, it's very unlikely that you can do this in polynomial time. So the second theorem essentially says it's, in general, it seems to be hard. Under certain assumptions, I'm sure it's not the case, but in the more general setting, it's unlikely that you can detect backdoors in polynomial time. Among those backdoors, it seems that those that are affect a small subset of the input features seem to be the most effective. And these are the ones that we call edge case backdoors. So this is the attack of the tail. So let me try to motivate this. So let's say that we have a federated trained classifier that, among other things, classifies images of planes. And the train and tested do not contain any images with a Aegean airplane. So Aegean is a really, really nice Greek airline. But let's assume that you won't find any of those images in the train and test set. And then the adversary says, look, I will collect a bunch of Aegean images of planes, which are otherwise looking perfectly normal. They look like planes. And I will mislabel them as garbage scans. And this is actually a true label from ImageNet. So you can find garbage scans on ImageNet. So the hope of the adversary is that if they do data poisoning, at inference time, maybe a user will take a picture of an Aegean airplane, and then it will be labeled as a garbage scan. And kind of the point of these types of attacks is not that I'm going to completely destroy the accuracy of the model for every subclass, but you will have rare, but however offensive and sort of bad business failures that as a service provider, I guess you would like to avoid, right? So these are kind of like rare failures that are essentially built, or rare backdoors that are built on top of edge case examples that, again, are normal, natural examples in the distribution, but they're not, they're unlikely to be found in the training or the test set of the users or the service provider. So we have a bunch of experiments in our paper, and we create those examples for image classification, digit classification, for contexts where the edge cases are built on, people that are wearing, Cretan costumes and like people of a specific ethnic background and so on. We're able to backdoor sentiment predictors on tasks that have to do with something with regards to, let's say, Greek directors that, you won't find too many of those in tweets. And then we're also able to backdoor text predictors when the context is rare, for example, by inserting negative words or words of negative connotation after, once you insert the word Athens, which is the capital of Greece. So I don't want to go into the details of the experiments, but we ran a lot of experiments, and kind of the main points of the experiments is that edge case backdoors seem to be more effective than generic backdoors, in the sense that if the adversary holds the vast majority of the data points, of the type of data points that are to be attacked, then these tend to be very effective. Unlike more generic backdoors, we black box type of data poisoning attacks only require 0.5% of the nodes to be adversarial, and white box model poisoning attacks require even less. The other interesting thing is that if you try to defend it, and this comes back to the point that Vitaly was saying, you will unfortunately also filter out and limit the accuracy of users that simply contain diverse data sets. So that's unfortunate, and it gives rise to an interesting robustness, accuracy, and fairness trade-off. And finally, which the last point was conjectured in the paper, I think the tutorial paper that came out of the workshop last year, models of higher capacity, they exhibit a higher propensity to edge case backdoors. So the more expressive the model is, the more vulnerable it is to these types of backdoors. I'm happy to discuss experiments that we have a lot in the paper, but just to wrap up, the point of this work is to show that there exist backdoors that current systems are vulnerable to. These are built on edge case datasets. And a lot of the results from our work, I think, highlight a very interesting trade-off between how robust your models are, the fairness that you can achieve, and the capacity of those models. And I think it sort of leaves open the question of, can we come up with provable defense mechanisms? And for that open question, I don't have any good ideas, and I would be very happy to chat more with you. But yeah, with that, I just would like to conclude.
Thanks, Dimitri. I think we have a few minutes for questions. I have a few questions, but I would like to give the audience the chance to go first. Brendan?
Sure. I just had a question about clarifying the setting for your results. Like, there's a big difference between like a cross-silo FL setting where you have, say, 10 banks participating in every round versus a cross-device FL setting where you have 1 billion devices and only a small fraction of them are even going to participate in a single round of training. So, in terms of, the statements about either, you're vulnerable to backdoors or not, I'm pretty sure that on the one end of that spectrum you are, and the other end of the spectrum you're probably not. And so I'm curious if your work shed some light on, where, in what regimes, do these results apply, basically?
Yeah, so that's a great question. So we basically tested them on the cross-device setting, and the number of devices, I think, ranged from like 40 to like 1,000 or something. But of course, if you only have 3 users, I'm not sure exactly what the result would be, but I would guess because if one out of those 3 users is more, is whatever adversarial, I would imagine that it's more likely for those backdoors to be more effective. And as you have more users and less of those, smaller fraction of those becomes or is adversarial, I would assume, and we see that in the paper that these backdoors become more and more weak. So it very much is a function of not so much how many users you have, but the fraction of them, how many of them is adversarial. And it seems that if 1% or more are adversarial, and this is something that Eugene had in his paper as well, then it seems to be feasible to insert these types of backdoors.
Yeah, the fraction makes sense. I think the difference is that, compromising 1% of 100 clients as pretty reasonable, compromising 1% of a billion Android devices. Like, you've got a bigger problem than backdoors once you have that problem.
Yeah, for sure.
A follow-up question that I have is, in your theorem that you mentioned, I was wondering what is specific to FL? It seems like it's a general result that applies to any training process, right?
Yeah, that's correct. So there's nothing really. So this is more. This has to do with general backdoors, like our data and model poisoning, right? So there's nothing in particular that's specific to federated learning. I mean, there are maybe, yeah. The only thing that can be tailored to federated learning is that you have multiple models, and some of those theorems take advantage of having multiple models. But you're right that this is basically checking whether a function has some particular value for a subset of the input. So absolutely right.
Okay, we're on time for this. We want to go back to Karan, but Tirtha, you wanted to say something?
I had a question in terms of this one follow-up question on the 1% result. So asymptotically, if n is the number of users, for Byzantine attacks, people know that if alpha fraction of users are corrupted, you can change your model by something like alpha n. Do you know if similar results hold for backdoor, and in particular, can anything be done with sublinear number of users? Like if smaller of n users are corrupted, is it still possible to insert like a backdoor attack?
So in the unconstrained case where the service provider does nothing, you can do what Eugene did, and you have just a single user that replaces the model. So the answer is yes, but if you start restricting this, it's unclear. So I think, if you say, okay, one user can't replace the model, or I can't make a change that's like a billion times bigger than an update that somebody else is trying to insert, then there's no direct answer. I think it requires a little bit more thinking, but I think it's a great question. Yeah.
All right.
So I think we can continue this discussion over Dory. It's very important, but I would like to give Karan the chance to finish his presentation. So
Thank you.
Hopefully Wi-Fi is not going to fail us again.
Yeah, sorry, I'm in an extremely Wi-Fi dense neighborhood, so there's so many networks that the list doesn't even finish. But yeah, so I don't actually know where I was in the talk, so please stop me, Peter, when I get to the slide that I was on. Is it at this or after this?
I think you were here.
Here, okay, great. So let me just go back to this one. So our starting point, I hope everybody remembers the first 5 slides. The starting point is private information retrieval, where a user has an index and wants to retrieve the item from a server's data set. And this is already well understood and well studied, and it's cheap for the user to execute this kind of cryptographic protocol. So our first step is going to be to go to keyword peer, which allows the user, instead of doing an index, to provide an ID or a keyword to query against the server's database, and to get back either the associated weight, in the case it was in the dataset, or to get back some garbage value. So this is our first step, and this step is actually easy, but the big problem is that this garbage value that comes back when X is not in the dataset. And so the main technically difficult part in our work is actually getting rid of this garbage value and replacing it with a default value that's specified by the server. So this is a thing that we call pure with default. So in the case you're in the set, you get back the associated rate. Otherwise, you get a server specified default. And actually, we add a couple more things to this. So we allow the user to insert a value in here. So you'll get back either the product of the value and the associated value from the server, or you get back the default. And in fact, the final thing is, we make it so that the user gets back the value masked with a random mask. And so this random mask is going to make it so that, and the random mask is chosen by the server. And this random mask is going to make it so that the user won't be able to tell whether it got one type of result or the other type of result. So it either gets a masked default value or it gets a masked product of the weights. And so once we've constructed this thing, it actually turns out to be pretty straightforward to get the functionality that we cared about. And at a high level, the idea is that the user is going to execute an extended peer with default on each of its rows in its database, and get back either a masked product of associated weights or a masked default value. And the default value we're always going to use at the server is 0. And so the user can simply sum up all of the things that it retrieved, and the server will sum up all the masks that it's used in each of the iterations, and then add some noise to that, and then send that sum of masks back to the user, who subtracts the masks and now gets back exactly the value that the user wanted. And so this is pretty much exactly what we're doing in the paper. And the details are in the paper if you're curious. So I just wanted to highlight like one thing about our costs. So basically our costs go really well as the difference in the devices input size and the server's input size become more and more disparate. So here we have 3 graphs that show like as you increase the server's data size from hundreds of millions to a billion, like what happens to the communication cost. So basically our solution is the red line. So our costs grow most slowly compared to other works as the server's data size grows while the user's data size remains the same. And the y-axis is actually log scale. So actually the other works grow a lot faster than our work, than it might seem. Yeah, and there are some extensions possible on what functionality we can compute. Like we talked about dot product in the work. Like we were focused on dot product because we saw clear applications for it. But basically, if you don't want to do dot product, if you don't want the product of the weights, you can do some other function of the weight from the user and the weight from the server. And the restriction, if you use our technique, is that this F has to be supported by a homomorphic encryption scheme. So a single multiplication is easily supported. Some other functions would also be supported. And then if you don't want to do a sum across these values, but you want to do some other function G, then we can support different kinds of Gs, and the G has to be compatible with whatever masking scheme you used or the secret sharing scheme that we use. And at some extra cost, you can do any generic function G. And then in terms of other applications, I hope you'll tell us. Yeah, and thank you.
Thanks, Karan. Do we have questions for Karan?
So, Karan,
Yeah.
so is the domain of the indexes arbitrarily large? Like, are these like 64-bit numbers or?
Yeah, it's like we think it's exponential, and then yeah, exactly. So yeah, 2 to the 64 domain or something, 2 to the 120. Yeah.
So it's exactly like querying a map data structure.
Exactly. Yeah.
Karan, I was wondering, is this the first peer approach for this problem? Was this problem addressed differently before?
Yeah. So basically, so if you, I'm not sure I've fully followed the question. Are you saying like, does peer not solve this problem immediately, or are you saying like, how did people do it before this work?
Yeah. How do people do it before? Because your approach is to to extend peer, to add these extra things on top of it.
Yeah. So the thing is, other works did it either with less privacy or did it with more cost in the case of asymmetric input sizes. So in the case of less privacy, you would either reveal exactly which items were in common or this number of items in common or something like that. And in the other case where you had the full privacy, the device would incur costs proportional to the server's data set, which is really high if the server's data set is large. Yeah, that's a good question.
So how hard would it be to extend this to the symmetric case where the database is encrypted?
The database is encrypted with the...
So here in peer, the server can see the database. So in some people tend to call it symmetric case for peer, the client would upload an encrypted database to the server, and not even the server would know what's there, right?
I think it would extend straightforwardly. The problem is that I'm not sure. Okay, so you're saying here it's kind of like an outsourcing solution. Like a client wants to one-time upload this database. And
oblivious transfer. You can call it oblivious transfer in also.
Yeah, that's a good question. I think the problem is once there's that extra layer of encryption on the server's data set, it's very hard to do anything with the client's input. Like you can't.
So you need homomorphism.
Yeah, exactly.
I see.
Yeah, but do you have an application in mind for this, or maybe we can talk offline?
Yeah. So yeah.
In the interest of time, I think. Tirtha, can you present? Thanks so much, Karan, and sorry about the technical issues. Again, we are hoping to continue having these discussions and questions over Dory, so please feel free to post questions on Dory.
Hi, everyone. Can you see my screen?
Yes.
Okay. Hi, my name is Kirka. I'll be talking about learning discrete distributions, users versus item level privacy. This is joint work with Johan, who is a PhD student at Cornell, with Felix, Sanjeev, and Michael, and all of us are at Google Research in New York. So let me give you a brief overview of differential privacy. So consider you have a mechanism or an algorithm, calligraphic M. Think of this as an algorithm to learn neural network, parameters of some Gaussian distribution or something like that. We call a mechanism M epsilon delta differentially private if its output for two neighboring data sets differ at most by e to the epsilon with probability 1 minus delta. If you haven't heard this definition before, no, I won't spend too much time going over it, but I would like to highlight a few facts. One is we are going to look at global differential privacy, meaning we ensure that the output of the mechanism M is differentially private. So if you learn a neural network, the neural network is differentially private. But we are not privatizing the actual data set itself. Typically, to implement this, one needs a trustworthy central server. In the absence of it, you can use something like secure aggregation or shuffling mechanisms to get the same effect. A key aspect of this definition is neighboring data sets. Like, what do we mean by two data sets are neighbors? And that's the focus of this talk. Typically, differential privacy is studied with item level privacy, where two data sets differ in one single item. So think of an application where you want to count like a distribution of words. So imagine you have two data sets, D and D prime, each having 4 users. In the first case, user 4 has an SSN. In the second case, user has a word I. So since the difference is they just differ in one user, this protects the this is item level privacy. And typically, loosely speaking, item level privacy means you protect the privacy of a single item. I won't go into too much into details, but let's say how it works in federated learning. In federated learning, typically users don't have one item, but many items. Think of an example such as learning distribution of words from a mobile keyboard. Some users type 1 word, some users type hundreds, and some may even go to thousands of words. In this case, if you directly use item level privacy definition, then the two data sets written here, D and D prime, are neighbors because they differ by one item of user 4. But however, notice that since user 4 uses the same word many, many times, even though it offers item level privacy, the bounds are a bit vacuous because you're not protecting overall privacy of a single user, but you just care about the entry of a single word. To overcome this, user-level privacy has been defined. Here, the idea is that two data sets are neighbors if they differ in data of a single user. So here, notice that instead of replacing just one single item of a user, all the words of a user can be replaced by something else. And since this offers more privacy, it's much harder to achieve. So therefore, understanding the actual trade-off between privacy and utility becomes interesting. In particular, how hard is it to achieve user-level differential privacy compared to item-level differential privacy? To understand this question, we look at a very simple statistical problem of learning discrete distributions. So here is the setting. So there is an unknown distribution P over K symbols. Think of this as like words of a vocabulary. And there are S users. And each user for this talk, assume has exactly M samples. So the total number of words we have is S times M. And the goal is to learn this unknown distribution P to a total variation distance of alpha. And we want to understand how many users we need to learn this with user-level privacy with some parameters epsilon and delta. So to do that, let's go take a step back and look at how many users we need to learn it with item-level privacy. Typically, the way it works is you compute the count of each symbol and you normalize it to get a probability distribution, and you add some appropriate Laplace or Gaussian noise. For example, here, in this particular example, if we want the probability of the word high, it appears twice, and there are 4 users. So the probability is half without privacy. But if you want differential privacy, you add like a Laplace noise of 1/4 epsilon. One can analyze this scheme, and it's not difficult to show that the number of users scales as k by alpha square plus k by alpha epsilon. Here, k is the number of symbols, alpha is the target total variation distance, and epsilon is the privacy parameter. I'll show 3 equations of this kind. So let me just explain how it looks. The first term, k by alpha square, is the statistical.
I don't mean to interrupt, but I just wanted to give you a heads up, 4 minutes heads up.
Okay, thanks. So the first term, k by alpha square, is the statistical complexity. The second term, k by alpha epsilon, is the privacy penalty you pay to get epsilon differential privacy. If you directly try to use Laplace or Laplace mechanism for user level privacy, you do the same thing. You compute the count of the word, you divide by total number of words, and you add appropriate Laplace noise. One can analyze this scheme, and it turns out, again, the number of users scales as k by m alpha square plus k by alpha epsilon. It looks very similar to item level privacy, except the statistical sample complexity goes down by a factor of 1 by m, which makes sense because if you have more and more users, you need fewer samples. More and more samples per user, you need fewer number of users. But somewhat surprisingly, the privacy complexity or the privacy penalty is independent of m, meaning even if every user has infinitely many samples, the total number of users you need remains a constant. So we tried various algorithms like Gaussian mechanisms, some sampling-based algorithms, and so on. And turns out all of them have the same problem. The privacy complexity is independent of m. We ended up showing like a rigorous information theoretic lower bound, which shows that for broad class of epsilon delta algorithms, the privacy complexity is independent of m. So a natural question is to say whether this can be improved by a newer algorithm. And the answer is yes. We propose a polynomial time epsilon delta algorithm where it achieves the optimal statistical rate, and the privacy complexity now scales as 1 by square root m, where m is the number of samples per user. We also show that this is almost optimal by showing a matching lower bound, just kind of giving like a precise trade-off between privacy penalty and the sample complexity.
Because we have 2 minutes, I wanted to make sure we also
I'm done, yeah.
All right, okay, cool. Sorry about that. We're just okay. So do we have questions for Tirtha? I have one question, but I want to make sure I give others the opportunity to ask. So my question, Tirtha, is you didn't get the chance to present the algorithm of how we can achieve this improvement by root m, but is it compatible with federated learning, or in this specific case, federated analytics at a high level? Can we use it?
It is compatible, but I wouldn't say it's a practical algorithm. Like you can recast it as a federated algorithm where you at each step you do something with secure aggregation and so on. But unfortunately, the algorithm is not super practical. Like we didn't analyze the constants and so on.
So for federated analytics, there's still this open problem of how can we get this root m improvement with a practical algorithm?
Correct, yes.
Nice. Any other quick question for Tirtha?
Yeah. So you have this dependency of 1 over root m for privacy. And if you have a heterogeneity, so like if each user has different number of sample, how does that change?
It's a great question. We don't know that answer. Our assumption is that all users have data from the same distribution. It's an excellent question.
But your algorithm still applies to that setting, but it's not clear what's the dependency.
No, the algorithm won't work. The guarantees don't hold.
I see. Okay.
Yeah.
Cool.
All right. So in the interest of time, we're going to switch to Arita. Arita, can you present?
Does that work?
Yeah, we can see your screen. Thanks.
Great. Okay. So this is a slightly different talk from certainly Tirtha's talk, which is very theoretical and the kind I like. But Arizona is at the forefront of a COVID-19 implosion here, and some of us started working on looking at building an app that could go into phones of 80,000 students at ASU. So that's the goal, and this is joint work with my colleague Nitru, who was an intern at Google, but she's now going to join ASU. She's a cryptographer, Mingxia, who's a distributed computation person, and Visar Berisha, who's a healthcare analytics person. I don't really have a lot of results. What I have is a framework that we've started implementing, and I'll talk about it and would love feedback on your thoughts on any part of it. So the key idea of our work is we want to improve the existing, and in this context, we're talking about Apple and Google's contact tracing app, which is based on Bluetooth. So we want to add GPS to it so we can sort of use the GPS to do, say, private histogram computation of infected hotspots. The other big part of this work is that we want to do on-device learning and come up with a risk score for COVID-19 that's going to be based on a bunch of things: baseline risk, mobility, phonation, and so on. And ultimately, the holy grail of this work is really putting this in ASU's mobile app. Okay, so this is a visualization. We'll be using both a Bluetooth and GPS, and the key idea is to do secure aggregation and privately learn infected hotspots, use the risk also to build that hotspot data better, and then develop some kinds of risk models locally on the device using federated learning. So I'll get into some of the details a little bit. On the contact tracing side, what we want to do is say 2 users, A and B, both have installed this app on their phones, 2 students at ASU. When they come in contact with each other, the Bluetooth part of the contact tracing app will communicate peer-to-peer, and the GPS part will be used to store locally the location logs. If one of them, say A, gets infected, A now, or a trusted third party like a healthcare provider, will send, instead of just sending the Bluetooth coordinate, key or token, will now use the Bluetooth key code to encrypt the GPS and send it to the server. And the whole point of doing this is then you can obliviously learn when, where, and whom A has met. And then so B, who's been in touch with A, will be notified that somebody she's been in touch with is COVID positive. So one of the things this does, it alleviates this replay problem that's an attack that's possible with Bluetooth-based contact tracing. How do we do infected hotspot evaluation? So suppose it's on ASU campus, you could sort of have all the buildings as a very long binary vector. So you would start off with all zeros, assuming nobody's infected. But as you go along, if somebody is infected, this binary vector that they send up securely to the server would have those locations tagged as 1. Right? So the server is just then going to encrypt these aggregate these encrypted vectors from infected users. So this way you get a sense of the infected hotspots. There's a natural problem here. If you were to scale this from, say, an ASU campus to states, cities, counties, countries, is how big does this vector get? And that's a genuine problem that I think my collaborator, is the one who's working on these parts, is considering using heavy hitters to threshold what do you aggregate on. All right, so on the device side, what we want to do is to give some kind of interpretable risk assessments. So you could look at risk assessment as having 3 parts to it. So when you download this app, maybe you take a survey, something like what closedloop.ai is doing right now. It'll be based on your basic health record. Do you have diabetes, heart diseases, and so on? That comes up with a baseline risk. As you move around, we could do mobility prediction and alert the user to maybe not just infected hotspots, but regular hotspots of people that are aggregating in locations. And that could be more periodic updates on risk. And the last could be, if you are perhaps worried about being exposed, could you use on-device learning to do some kinds of assessment of your own personal risk? So that's where we're going to use speech or phonation-based risks. Very briefly on the vulnerability index, these folks at closedloop.ai have developed something that uses people with respiratory disorders and their hospitalization rates to come up with a model. So the reality here is you don't have enough COVID-19 data, right? And you don't have label data on it. So they're using hospitalization as a proxy for high risk. What we can do at ASU is actually, ASU has been doing a lot of testing, and every test involves a survey. Our goal is to actually use that data to directly predict a risk better than what this does. On the mobility side, the goal is to do to actually do federated learning, to learn a model that will predict your mobility as you're going along. But the whole part of predicting that mobility is to also, if you were within, say, 100 meters of a location on campus that's tagged as important, then you can share securely your prediction with the server, and that can aggregate to come up with mobility-based hotspots. And so based on that, one can come up with some kind of a risk prediction, a risk index. All of this has to be interpretable to the user in terms of saying, look, this is either an infected hotspot, which the server already has, or there's a lot of traffic here. You may not want to go at this time. So that's the kind of thing we want to do. The last part is to alert users who may already be concerned. And there's enough data out there that says that when you phonate, so that phonation patterns are actually related to respiratory symptoms, because speech engages the respiratory system. So the key idea here is to do some kind of feature extraction and then come up with a prediction of risk, again, using existing age and gender-based norms as kind of ground truth data here, right? So ultimately, I think we would like to predict one cumulative risk. We're still trying to figure this out. We're still working on these parts right now, and it could very well be that you just put out 3 types of risks. But if you did any kind of a cumulative risk, including the mobility risk, which needs federated learning, any cumulative risk will also need that. So there's a lot of engineering problems here. I think if I come back in 4 months, I would have more details, but right now this is our broad idea. And as I told you before, we're actually going to deploy this in stages, starting with just known users that we pay to actually test the app out. I'm sure all of you know that there's lots of challenges here. Certainly with Bluetooth and GPS, there are these issues of accuracy and proximity. In terms of aggregating for a number of hotspots, that's already a very large problem. For the Bluetooth versus GPS, if you want to continually use more and more Bluetooth codes, there's a scalability problem, even though you give better privacy guarantees in that case.
Sorry,
on the device, setting mobility is a big issue in terms of prediction. What I mean by that is how well do we predict your mobility patterns? We need more surveys if we have to do better risk aggregation locally and so on. So I'm going to stop right here and let you guys ask me questions.
Cool. We're actually out of time, but maybe if somebody has comments or
I have a quick question.
Yeah, sure.
Hey, Lalitha, how's it going? This is Dimitri from Madison. So yeah, I have a question related to like a social challenge of these contact tracers. So here in Madison, like human contact tracers had a big problem with students in the whatever, like 18 to 25 age bracket, where they would not reveal the social groups they were interacting with or the places they would be at. And this coupled with the fact that a lot of people are not even wearing masks, kind of like implies that it may be challenging for folks to actually, use these, these apps, right? So I'm wondering if you only have a very small sample of the population, how effective these contact tracers are.
Great question. One of the things I'm hoping universities will do, like they've been claiming now, is that they are actually going to have strict disciplinary methods if they are found partying. But that aside, the one thing I didn't mention on the technical challenges, I've developed a class of like tunable loss functions that are very sensitive to either the robustness issues or to like class imbalances. So one of the things we do want to do for the real COVID data we have, and keep in mind for the data that Stanford just used, it's 1% of the people out of 10,000 that are COVID positive. So how do you boost them up? That's the kind of stuff we can do technically. I'm hoping in about a few months we'll have those results, and I'll email you.
Cool. All right. So
mechanisms. Sorry.
Hi, Lalita. I just have one quick comment. Great work, great plan. So we actually also starting a React or Rapid project, sharing some of the similar goals. So I would love to talk more offline.
Yeah, I'm sure a lot of people have a lot of things to say to Lalita. I wanted to also ask a few questions. So let's have these conversations on Dory or via emails. For now, let's please join the breakout sessions. Keep in mind that we have 6 as opposed to 8. You can find, Jennifer just sent the links to the breakout sessions. So we're going to do short breakout sessions and then reconvene for closing notes. So please stay with us for the next few minutes. Thanks to all speakers, and thank you for attending this session.